All right, now let's move on to the second topic, I/O management. Now this is how OS deals with external devices that engage in I/O activity with the system. Now, let's first talk about external devices. Like Windows, Linux deals with the external devices via device drivers. However, you can't forget the Linux belief. Everything, and I mean everything, is a file or a process. Linux views device drivers as normal files. Users can open access channels to an external device same way they could open a text file. So where are they stored? Stay tuned for the final topic. External device classifications. In real world, external devices are classified as human readable, machine readable, and communication. In Linux, they are described as block device, character device, and network device. Block device, they are devices that read blocks of data and randomly accessed. Main operations done on these block devices are read, write block of data to disk. Transfers are done in disks and blocks. Blocks refer to block of unit in which kernel performs the I/O. When block of data is read into memory, it is stored into a buffer. Request manager maintains that buffer. This is a structure of a device driver block. You'll see some stuff such as TTY driver and line discipline, which we will explain next in the upcoming slides. Now let's look at request manager. It is a software that manages buffer by keeping a list of requests for each block device driver separately. Main algorithm that used by request manager prior to 2.6, a cscan. Requests maintained in sorted order of increasing starting sector number. Requests accepted for processing by block device are not removed, and they are only removed when I/O is complete. Now, what's the main problem? Starvation. Since some requests are only removed when I/O is complete, other requests are going to have to wait. So solution to the starvation by cscan? Deadline I/O scheduler. It associates a deadline with each request so that all requests get a chance for I/O before deadline. What are the implementation details? It uses three queues: sorted queue for pending I/O by sector number, read queue for read operation, ordered by the deadline, and write queue for write operation, ordered by the deadline. So in deadline scheduler, I/O request is placed in both sorted queues and one read or write queue, depending on the type of job it is. So each request will be placed in the sorted queue, and depending on if they are a read or a write, will be placed on the appropriate queue. I/O operation occurs from a sorted queue, but if deadline is reached for any request in the read or write queue, I/O operation will be rescheduled from one of the write or read queue containing the expired request. No starvation. Everyone eats. So why would this work? So instead of keep finishing off one request to the I/O, a thing or an attribute known as the deadline will force the scheduler to do the request to do other requests. All right, now moving on to character devices. Unlike block devices, these are devices dealing with single unit of data at a time and process data sequentially. Real life example, keyboard or mouse. Think about typing each key and how data is being received. Character devices do not support random access to fixed blocks of data. They are responsible for providing functions, and also character devices are responsible for providing functions that implement file I/O operations if they are to be registered to Linux kernel. So pretty much kernel just passes the request to the device. Kernel does not do any processing. A real world example would be a printer job. The kernel merely just sends the printer job request to the printer. It does not do any processing. Once the printer device receives the request and starts its job, the kernel cannot recall that job or make any modifications to it. Only exception to the last rule for character device, which I have mentioned, was providing functions that implement file I/O operations such as read or write. The only exceptions to those are character devices that implement terminal devices. A such thing as TTY structures. TTY is a type of device file that implements a number of additional commands beyond read or write. input and output controls, system controls. System calls for device-specific I/O. Main job is to provide buffering and flow control in data streams from terminal device and send in to the line discipline. What is a line discipline? There are many layers. Upper layer is to provide character device interface. Lower hardware driver layer is to communicate with hardware character device interface. And middle line discipline layer is to implement common behavior to terminal devices. So the most common line discipline is a TTY discipline. It decides which process data should be attached, detached from terminal device, STD in, STD out. Example is when using terminal and user inputs the kill character. Right, now we look at the device driver block structure, and you can see we have the block device file, and then on the bottom right, we see the character device driver. On top of that, we see the TTY driver and the line discipline. And then on top of that, we see the character device file. So those are the three layers I was talking about. The upper layer, which is the character device file, middle layer, which is the line discipline, and the bottom layer, which is the character device driver. Now, onto the third type of device, network device. They are managed by Linux's kernel networking subsystem. Users are not able to transfer data from network devices and must go through the networking subsystem. So in the Linux networking subsystem, there's three layers: socket, protocol, and network device driver. The network device, so the socket, the three networking subsystems. The socket interface deals with network address for networking protocols. And then the protocol drivers, the main operation deals with packets. All data in this layer is tagged with ID specifying which network protocols. And then finally, the network device driver. Communication between different network layers is done by a set of pointers to a single contiguous block of memory where network packets are made, known as skbuf. In Linux, TCP and IP suite is very important. Now to the big topic of disk scheduling. I/O requests for the disk must be scheduled by the OS. Similar to CPU scheduling, there are disk schedules that use different types of policies which implement different algorithms. They can be changed at runtime. Down below is an example of trying to change a disk scheduling. Look at the file path and see where the scheduler is, the disk schedules are stored. So some of the most common types of disk scheduling in Linux are NOOP or NOOP. It's a basic first come first serve, request sorted by sector number. It's good for random access block devices and is best for memory backed block devices. Got deadline, reads block processes, mandates read requests be served within 500 seconds, and write within 5 seconds. If something expires, start serving them in sorted order. Main upside is lightweight, and its focus is dealing with latency. Completely fair queuing is the default currently in most Linux distro. It is sorted by sector number in the disk. Maintains process level fairness. How does it implement? It keeps separated sorted queue for each process, round robin with quantum for each queue. It enforces system-wide fairness of I/O bandwidth. Anticipatory is removed in 2.6.33. It's similar to deadline, but an additional constraint of waiting 6 milliseconds for new requests to maintain sort. Elevator algorithm, which has no longer been used since Linux 2.6 and has been replaced by the aforementioned deadline I/O and anticipatory I/O. So we're looking at this is an I/O overview. In the very bottom there, we have the hardware. On top, we have the interrupt handlers, and on top of that, we have the device drivers, which is talked about. On top of that, device independent software, and then user processes.